So take a look at this function here. I can start at some point and trace this function with a pen or a pencil, and I wouldn't have to lift my pencil off the page at all because there are no breaks, there are no gaps, there are no holes, right? And even though we only have a little part of this function, it doesn't go to the infinities, you know that it continues, just as smoothly to either infinity. All right? So that's a continuous function. Continuous functions are used to describe how a body moves through space. Okay? It's also used to describe how the speed of a chemical reaction changes with time. Okay? All right. So we can talk about continuity throughout the entire life of a function. Like this one, for example, here is an example of remember when we were talking about like the power function? This would be like an x cubed. So this is a function that is an x cubed function. And if we were to talk about continuity throughout the life of this function, this would be continuous. Okay? Now, in a lot of cases, that's beneficial, that's fine, that's perfect. Often in calculus, we think it's important to talk about continuity not over its entire life, but at a certain point. So for example, a function can be continuous everywhere except for one tiny little point. There might be a removable discontinuity, a hole, and that will make or break everything. So it's important that a lot of times we talk about continuity at a point. Now, when we're talking about a point, we can differentiate it into two different types. We have continuity at an interior point and then continuity at an end point. Okay, so what do I mean by that? Most of the time in calculus, we're not going to take functions from negative infinity to positive infinity. We don't care about negative infinity to positive infinity. Most of the time, we're going to take functions from A to B. Okay? So I will take this function, for example, and I'll say, okay, the only parts of this that apply to me are from A to B. Okay? Now, if I zoom in here, and if I have A to B right here, then I have created endpoints. Okay? So this is an endpoint here, and this is another endpoint here. All right? So I've created endpoints here. Now, if I talk about an interior point, it's all the points from inside one endpoint to inside the other endpoint. And then so that's an interior point. And then an endpoint would be the actual points. Okay? Does that make sense? So a function is continuous at an interior point if its domain, right? So basically if it lies in between A and B. Okay? And if it's continuous if within its domain the limit at every point is the same as the value of that point. So remember how we're doing, okay, limit is like it approaches 3, but does it actually get to 3? No. We're like, okay, for the limit it doesn't matter. For continuity it does matter. So what we want is it's approaching 3. Cool. Does it get to 3? Yes. Okay, now it's continuous. And then at an endpoint is, so if I'm looking at this endpoint, if I'm looking at the endpoint towards the right, if I approach it from the next side, so the limit from the negative side, is that equal to its value? And then the endpoint on the left is the endpoint from the positive side equal to the value at that point. So those are limits at an endpoint. All right. So what happens if it's not continuous? If a function is not continuous at a point C, then we say it's discontinuous at C. All right? And then C is a point of discontinuity. Okay? Now, C does not need to be in the domain of F. Okay? That's important because that's where our discontinuities are going to happen. Okay? All right. So let's reiterate what we just said here. Okay? Suppose I want to talk about, is this function continuous at x equals 0. Okay? So, is there a limit as x approaches 0? As x approaches 0, is there a limit? Does it approach the same place from the right and the left? Yes. So there is a limit as x approaches 0. Now, how about f of 0? Is that the same value as the limit? No. F of 0, it is the same value, right? Because it's approaching that same point. Because they're the same, then yes, this is continuous at x equals 0. Yeah.
So if the limit of the function is equal to the function with the number in it, if they're equal to each other, then it's
continuous. Okay. So that was if it was continuous. So let's talk about what if something is not continuous. Okay? All right. So take a look at this one. Let's look at the limit as x approaches 0 from the negative side, and let's look at the limit of f of x as x approaches 0 from the positive side. All right? Are these two equal to each other? No. Okay, so x approaches 0 is here. Yeah. Are they approaching the same place? Yeah. Yeah. So those are equal to each other. Okay? Now, what about f of 0? Is it the same value as that? No. So this is equal to 1, right? The limit there is equal to 1, but what's f of 0? 2. So these are not the same. That means there is a discontinuity. Okay, the type of
there's like a really small dot.
There is a point here. There's a hole here, and then f of 0 is 2.
Oh, I didn't see that.
Okay, you can see it on the page probably, but even if you can't see it, can you see the hole? Right? Yeah. Even if that dot wasn't there, even if that hole, it was just that hole, and the f of 2 did not exist, you would still say, okay, they're not equal, so it's not continuous there. Yeah.
It's only 2 because there is a point at 2.
Correct.
Yeah.
All right. So that's one type of discontinuity where the limit from the left equals the limit from the right, but the actual value of the function isn't that value. Okay?
Wait, is there an open circle on the right?
There is an open circle here, if you look on your sheet, and then there's a closed circle there. Okay? All right, so take a look at this one. The limit as x approaches 0 from the negative side of f of x, and look at the limit as x approaches 0 from the positive side of f of x. Are those two limits equal to each other?
No.
No, they're not equal, so that's another type of discontinuity. We call that a jump discontinuity. Okay, so in the first case, the limits were equal, but they weren't equal to the value at that point. In the second case, the limits are not even equal. That's not even cool. Okay, this case, the limit as x approaches 0 from the negative side of f of x, and then let's take a look at the limit as x approaches 0 from the positive side. So as x approaches 0 from the negative side, what's the limit? As x approaches 0 from the negative side? Infinity. What about as x approaches 0 from the positive? I wrote that wrong. 0 from the positive side, it's infinity. So here, they both approach infinity. They're not approaching a finite number. So that's another discontinuity. We call this an infinite discontinuity. Right. In this case, you have vertical asymptotes. So basically, so this is a third type where the limits aren't even a real number. It's just infinity. Okay, the fourth type is an oscillating discontinuity. So take a look at this. What's happening? Where is the graph as x approaches 0? It's going up. There is no way to know at what, like where it is as you approach 0 because it's oscillating so quickly. So that's an oscillating discontinuity. Okay? All right, so again, if you were to trace any of these, Like, look at, if you had to trace the first one, you would have to take your pencil off the page at the hole. The second one, like, is a huge jump. The third one, it goes off the page. You don't know where it goes. The fourth one, you can't even trace that one, right? So if you just hold that as a rule of thumb, then you could figure out what's continuous. Yes?
So because it's untraceable, we assume that.
Correct, because there is no way to find the limit. Mathematically, there is no way to find the limit. Okay? All right, so here, it says to find the intervals of continuity and the points of discontinuity of the function. So, like, a function might be discontinuous somewhere, but it's continuous everywhere else. It's important to define where it is continuous. Okay, so, in order to be able to do this, so remember, we can have discontinuities where we have vertical asymptotes, and we can have discontinuities where there are holes. We can figure out both of those algebraically if we just factored out the function and simplified and all that good stuff like we were doing in section 2. Okay, so let's factor this out. We get x plus 1 over x minus 2 and x minus 1. Now, does the x minus 2 cancel? Does the x minus 1 cancel? No. So from both of those, what do we get? Vertical asymptotes, right? Both of those give us vertical asymptotes because they don't cancel. So now, where do I have a vertical asymptote? Right. So I have discontinuities at x equals 2 and x equals 1. Okay, so let me write that in increasing order so it'll be easier for us to visualize. So now, let's visualize this for a minute. So this function, if it starts at negative infinity, it's all cool until we reach x equals 1, not cool. And then from 1 to 2, it's still okay. At 2, it's not okay. And then and after that, it's still cool. So where is it continuous? Right, negative infinity to 1.
And then 1 to 2.
And then 1 to 2.
And then 2 to infinity.
Correct. Okay? So, did we provide everything? So, intervals of continuity, check. Points of discontinuity, check. Type of discontinuity, they're both what type of discontinuities?
Jump.
Not jump.
Removable.
Not removable.
The other one.
Infinite.
Infinite.
Oh, because there's vertical.
Oh, we need a
Correct. Right.
There's vertical asymptotes.
Correct. If it was removable, if it was ones that we could cancel, then it would be removable. Because get it, you can physically remove it out of the equation. Okay? That's what I was trying to get at last time. And every time I say it, yeah. Every time I said there's an ah moment. So I like that. Cool. Okay.
Can you have more than one type of discontinuity?
Yes, you can. Okay.
That was an omelet.
Yeah.
How did you know those infinite?
Because they are, going back to section 2, this is a rational function. I wasn't able to cancel out the denominators. That means from the denominator, I get vertical asymptotes. And vertical asymptotes give me infinite discontinuities, like in this chart.
So whenever you have a vertical asymptote, you can have a
Correct.
And then when you cross them out, then it's removable.
Then it's a removable.
And then what about
Jump is, we'll see. Jump is, you're going to get jump mostly in the piecewise functions. Okay? All right. So take a look at this one. This is an absolute value graph. And I tell my students all the time, absolute value, okay, value V, the graph looks like a V. Okay? So absolute value graphs look like a V. It just so happens that the vertex is at x equals 1. But can you trace an absolute value graph without removing your pencil from the page? You can. So this is completely continuous. It's totally cool. So it's continuous on negative infinity to positive infinity, no discontinuities.
Is it usually like that?
Always.
Always.
No.
That's we have to write in our answer space.
Correct.
Right. Continuous on negative and positive.
Correct.
No.
Correct. Okay, next is ln. Okay? When it comes to ln, I'm not going to expect you to draw it by hand. So if we were to plug it on our calculator, there is a horizontal shift here. And it's going to look like this. Take my word on that one. Okay. So there's going to be a graph everywhere starting at 1 and going up, but it can never hit 1. All right. So it's going to be continuous on 1 to infinity, and there are no discontinuities. And it's good to know that ln logarithm graphs are always continuous in their domain, right? Their domain is never all real. They start one place and then they go on to infinity, but when they are alive, they're continuous. Yeah.
Doesn't the asymptote mean that, or why isn't there discontinuity at 1?
It never hits 1. It just starts at 1 and like it starts right after 1 and continues forever.
Okay.
You know what I mean? So because so its domain is 1 to infinity, and that's it. Like a discontinuity would be if within its domain it like started and stopped, or stopped and started.
Okay.
Okay?
So if there was like another part, the other side of the asymptote, then it'd be
Yeah,
it's
correct. Correct. Absolutely. Okay. So, all right, so take a look at this one. This is e to the 2 over x. We're used to seeing e to the 2x, which is continuous everywhere, negative to positive infinity. But this one, take a look at this. You have an x in a denominator. So still, x can never be 0. Okay? So just remember that. So now, again, this one, I'm not going to expect you to graph off the top of your head, but I would like to enter it here because I want to show you guys how to put it in your calculator. So y is equal to e to the power of 2 over x, and we're always going to do zoom 6 on these, right? So you have to make sure that 2 over x is in parentheses. All right, so take a look at this. It looks like there is a vertical asymptote where? At x equals 0. Okay, so it's continuous, negative infinity to 0, 0 to infinity. Okay, yes.
Oh, would that be jump?
No, it would.
Is it infinite?
It's infinite. So I'll tell you what, that's actually a glitch in the calculator, and believe it or not, not all calculators will show it that way. Some models of the calculator show it that way. So what you could do, in order to make sure that that's what it's like. So, okay, first of all, broadly speaking, whenever you have an asymptote like that on one side, it's never going to be that right before that asymptote, it just stops. It's like a dead end, right? Remember what I was saying before is if it goes off the screen here, then on the left-hand side, it's going to re-enter the screen here. So it's pretty much a glitch in the calculator. You can trace it and you can see that it actually goes further down. What you could also do is change the windows so you're going from negative 1 to 1 and see that it goes further down. You know what I mean? When the calculator zooms out like that, they just don't show it. Remember, it was a human being that wrote the algorithm to this years ago. So there are glitches. All right, so algorithm.
The code?
Right.
If the denominator is x, it can't be 0, right? So does that mean that 0 is always the first class?
Right. So you know that x should never equal 0. You know that something's going to happen at x equals 0, right? You just know. So discontinuity is at x equals 0, and it's an infinite discontinuity. Okay. Now, we got a piecewise function. Let's do the easy stuff. Okay? All right. So I'm going to start from the very bottom. When x is greater than 2, so I'm here. When x is greater than 2, it's negative x. Okay? So at x equals 2, what's the value? But when x equals 2, it's negative 2. Now, is it open or closed there? Open. And then it's negative x, right? Negative x goes which way? Well,
Why are you starting
Well,
now?
it's greater.
it's gonna go down. I'm just a matter of preference. So basically, it's gonna fall over like this. It's a matter of preference. I'm just starting from bottom up.
No,
I'm being
not
a,
because of that, because why is it, why do you start at -2 on the bottom and 2 over to the right?
so I'm graphing this one here, and that one is only active x equals 2 and on. So when x equals 2, I plug 2 into negative x, and it gives me -2, right? So at -2, I put an open circle, and negative x is a function that decreases from left to right, so it goes down that way with a slope of -1. Okay? Yes.
For this one, are we gonna use calculators?
Okay, so so this one you could do without, and I'm trying to show you how you could do it without. Okay? Now, take a look at this next one. Let me color code these things here. So this next one up from the bottom, it says x equals 4, but where?
At 2.
X equals 2, only at x equals 2. So at x equals 2, it's 4, and it's just a point. How cool is that? It is a closed circle because x equals 2 there. Come on, that's pretty cool. Okay? Now, from 0 to 2, so now we're here. From 0 to 2, x equals, it's x plus 1. So now, at x equals 2, what's the value of the red one? 3. Open circle though, thank you. Okay?
Nice.
Why is it open?
Because at here, it's just less than, not less than or equal to. Also, if we already put a closed point there, we can't have another closed point on that vertical line. It would not be a what?
Function.
Not be a function because it won't pass the vertical line test. Math just makes so much sense. If only life was like math, then it would just,
Then I would have a
we would be posty. Okay, let me do that other point and then I'll get you. Now, on the other end of this, at 0, what's the value?
1.
X equals 0, y equals 1, closed circle. Whoa. Okay, yes, Zach.
Okay, for negative x, why don't you go down 1 over 1?
I did. Down 1 and over 1. Down 1 and over 1.
Oh, so now you're gonna start at 2.
Because it's here the bound is from x equals 2. I put 2 here. I got -2.
Got it.
Okay. Now I left the best one for last. It's x squared plus 1. What does that look like?
Downward left.
Right, but it's negative x squared plus 1.
Showing now.
So it's a, right, okay, so now
I'm
look.
showing down, but starting at 1.
So now look, at x equals 0, what's the value of it?
It's
We can do that
1.
chart.
1. We don't have to do the chart because it's 1 point. And then at x equals -1, what's the value of it? 0. So it's here. Okay, so at x equals -1, open or closed? Closed. And now look, I have my 2 points, right? And in between, this looks like an upside down parabola. So you know what? There is no need for being that precise here. We're not doing brain surgery here. Just give it an arc, and that's it. You're good to go. Just give it an arc. Okay?
Wait, how did you get it to be at -1?
Here? Here, -1. You plug in -1 here, and it's -1 plus 1, 0. So it's -1 squared. That gives you +1. There was a minus here. -1 plus 1.
That gives you 0.
0, right. But when x is -1, y is 0.
Ah, I
When
see.
x is -1, y is 0.
So don't take this low part of the parabola.
How do you know that?
How do you know which one?
That when x is 0, y is 0.
Because that's how we get it. So you see how it's at x, the left endpoint is -1.
Between -1 and
Right.
Got it.
Okay, now, so let's get back. Does f of -1 exist?
Yes.
Yes. It's that green dot over there. Does the limit as x approaches 1 from the minus, oh, sorry, oh yeah, 1 from the minus side exists. So as x approaches 1 from the minus side, does that exist? Yes. Does the limit of f of x as x approaches 2 from the positive side, is that equal to f of 2? No. Is f continuous at x equals 0?
Yes. Yes. No.
So it's either yes or no.
Maybe.
How do we know? Okay. Limit x equals 0 from the minus side. Limit of f of x, x approaches 0 from the positive side. And then we have to look at f of 0. So, as x approaches 0 from the negative side, what do we get? 1. As x approaches 0 from the positive side, what do we get? F of 0? 1. Yes.
So if it was two separate answers, it would not be continuous.
Correct. If any one of those were different, then it would not be continuous.
So if you make that graph wrong, then like all the stuff.
Correct.
You don't get partial credit?
There's
Carry on?
always partial credit, but we're talking about full credit here.
Something like that could be on the test. The question is,
Of course. No, the quiz is on 2.1 and 2.2. Test, yes. Okay. Okay, so here's another one. Let's start in the right order this time. So the very top one, when x is less than 2, it's 3 minus x. So at x equals 2, how much is it? 1, and it's an open circle. And then the slope is minus 1. So this is going to be decreasing from the left. So it's going to look like this. Okay? Now, at x equals 2, it's 2. And then it's x over 2 when x is greater than 2. So what's x over 2 really? Exactly. Okay? Good. So these are the sorts of things that as calculus students I want you to be able to work through. So it's 1/2 x. Now, when x at 2, our value is what? 1. So it's right there. Open or closed? Open. Okay, right. So still open. Open and open, stay open. And then the slope is up 1 over 2. Oops. So it looks like that. Okay, so find each point of discontinuity. So where is there a discontinuity? At x equals 2. So A, discontinuity at x equals 2. Okay. Which of the discontinuities are removable? Is this a removable discontinuity?
Yes.
Yes, because it's just a whole. So x equals 2 is removable. Part of the reason for these exercises is also to show you proper notation of how you would provide your answer. Let me do this one, and then I can take your questions. So, okay, so now, if I had asked you to explain why there is a discontinuity, all right? Explain why there is a discontinuity. Okay, there should not be a question there, but fine. You would say the limit of f of x as x approaches 2 from the negative side. So there are 3 things we're looking at. Look, I'm just going to look at the 3 things we need to look at. So one is x approaches 2 from the negative side, one is x approaches 2 from the positive side, and then one is f of 2. Now, are the limits from the left and the right equal to each other? Yeah, so here we put an equal sign. Now, are those equal to f of 2? No, so here we put a not equal sign. Okay, now that we know continuity at a point, okay, if a function is continuous at every single point on an interval. So like, let's say we're looking at x equals 1 to 2. A whole interval from x equals 1 all the way to x equals 2. How many points are there in between? From x equals 1 all the way to x equals 2, there are like infinite number of points. So if x is continuous everywhere along that interval, at every single point along that interval, we say that the function is continuous on that interval. Okay? So a function is continuous on an interval if and only if it's continuous at every point of an interval. Okay, so that's what it means to be continuous on an interval. So we're pretty forgiving in calculus. A function can be discontinuous at some point, but if there is an interval where it's continuous, we're like, okay, look, at least it's continuous on this interval. Now, if we say the words continuous function, okay, f is a continuous function. So we're getting used to some terminology here. If we say the words continuous function, that implies it's continuous everywhere on its domain. Okay? Everywhere on its domain. Okay? All right. So a continuous function has a discount. So look at this one. Y equals 1 over x. It's continuous. It's not continuous from -1 to 1, but it's continuous everywhere else. All right. So we always like to reference where is something continuous. Okay. So these are some more properties, okay? Because we love properties. All right. So properties of continuous functions. So here f and g are separate functions. If you have two functions f and g, and they're both continuous at x equals c, then f plus g would be continuous, f minus g would be continuous. Why do we care about this? It's so many words and so many symbols. Take a look at this. So here it says explain why the given function is continuous, right? Okay. So how many different functions do you see here? 3? Yeah. So the biggest one is the sine function, right? Is sine continuous? Sine of x? Does it ever, like, can you trace sine of x forever without removing your pen? Yeah, so sine is continuous. What about x? What about x? F of x equals, y equals x. Is that continuous? What about x squared plus 1? That's a parabola. Is that continuous? Yeah. So if you have a composite function made of continuous functions, then the end result is continuous.
Like tan wouldn't be continuous. Right?
Correct. Okay? So this is continuous because the functions of which it is composed are continuous. Okay? Lots of writing. I mean, not lots of writing, but you know, there are lots of places in calculus where you actually have to write like English sentences to talk about mathy stuff. Okay?
And math is now like half letters.
Math is now like all letters, and yeah.